Nuclear fission, the colossal power unleashed from the atom, wasn't a sudden laboratory discovery at all. It was a terrifying, incomprehensible experimental observation, a baffling anomaly that stumped even the world's leading chemists. And the brilliant mind who finally deciphered it, who understood its true nature when no one else could, was a woman systematically written out of history. In the next few minutes, you will grasp the full, startling truth of Lise Meitner's absolutely crucial theoretical insight, a moment of profound scientific genius that didn't just observe nuclear fission, but definitively defined it. You will uncover precisely how societal prejudice and scientific politics deliberately sidelined her, denying her the Nobel Prize and obscuring her name from the history books that shaped generations. The standard narrative, the one you likely absorbed in school, attributes the discovery of nuclear fission squarely to Otto Hahn and Fritz Strassmann. The year was 1938, a tumultuous period on the brink of global war. In their Berlin laboratory, these two renowned German chemists were bombarding uranium nuclei with neutrons. What they expected to find were transuranic elements, heavier than uranium, a continuation of experiments that had defined the cutting edge of physics for years. But their results were, to put it mildly, deeply perplexing. They detected barium, an element far lighter than uranium, after the bombardment. Barium. How could a uranium atom, with its 92 protons, somehow transform into barium with only 56? The prevailing scientific wisdom of the time, championed by giants like Niels Bohr, held that an atomic nucleus, while potentially capable of shedding a few particles, was largely indivisible. The idea of an atom splitting into two roughly equal, lighter elements was considered utterly unthinkable. It challenged the very foundations of physics. As Hahn himself wrote to Meitner in December of 1938, describing the baffling barium detection, perhaps you can suggest some fantastic explanation. He was, in his own words, absolutely stumped. This wasn't a moment of triumphant discovery in the lab. It was a moment of profound scientific confusion, bordering on disbelief. The evidence in their beakers simply defied every established physical law they knew. This is where the history we've been told veers sharply from the actual evidence. What Hahn and Strassmann had observed was an experimental fact, undeniably significant, but they lacked the theoretical framework to explain it. They didn't understand what they were seeing. Enter Lise Meitner. By this point, Meitner, a brilliant Austrian Jewish physicist, Hahn's long-term collaborator and the head of the physics department at the Kaiser Wilhelm Society, had been forced to flee Nazi Germany. She was in exile in Sweden, deprived of her laboratory, her colleagues, and even her pension. Hahn's desperate letter, filled with experimental data and scientific bewilderment, reached her just before Christmas, and in a stroke of sheer intellectual brilliance, during a Christmas Eve walk in the snow with her nephew, fellow physicist Otto Frisch, Meitner had her eureka moment. They sat down on a log, pulling out a notepad and a pencil, and began to calculate. Frisch recounts the scene, Meitner meticulously drawing diagrams, her mind racing. She applied Niels Bohr's liquid drop model of the nucleus, visualizing the uranium nucleus as a wobbly, unstable droplet of liquid. When a neutron hit it, Meitner theorized, the droplet became so unstable it elongated and then split, like a water balloon rupturing into two smaller droplets, barium and krypton. But here was the crucial part. If you added up the masses of the resulting barium and krypton, they were slightly less than the original uranium atom. Where did that missing mass go? Meitner knew the answer. E equals mc twench. Albert Einstein's famous equation. That tiny difference in mass, she calculated, was converted into an absolutely colossal amount of energy, nearly 200 million electron volts per atom. This wasn't just observing a reaction. This was explaining the fundamental mechanism. This was defining nuclear fission. Frisch later coined the term fission after the biological process of cell division. Within weeks, on January 16, 1939, Meitner and Frisch published their theoretical explanation in the prestigious journal Nature. fundamentally transforming a confusing experimental observation into a profound scientific discovery that would reshape the world. The implications of this reevaluation run deep, fundamentally altering how we perceive the narrative of scientific progress, especially during the tumultuous 20th century. Hahn and Strassmann's experimental work was essential, yes, but it was Meitner's theoretical insight that provided the understanding, the intellectual leap that made sense of the inexplicable. It was her brain that turned baffling data into world-altering knowledge. Yet, when the Nobel Prize in Chemistry was awarded in 1944 for the discovery of the fission of heavy nuclei, it went solely to Otto Hahn. Meitner was conspicuously absent. Why? The reasons are complex, interwoven with personal ambition, institutional bias, and the dark shadow of Nazi Germany. Meitner, as a Jew, had been purged from her position, her name removed from publications Hahn co-authored with her after her flight. There was a prevailing, deeply ingrained sexism within the scientific establishment that often dismissed the intellectual contributions of women, especially theoretical work, as less significant than hands-on experimental results. The Nobel Committee, as chronicled by historians like Ruth Lewin Sim in her definitive biography, Lise Meitner, A Life in Physics, failed to fully grasp the theoretical nature of the discovery, overemphasizing the chemical aspect and downplaying the physics that Meitner provided. One Nobel Committee member even dismissed Meitner's explanation as mere interpretation. Do you truly believe, now knowing the full story, that an interpretation that unlocked the very nature of atomic power could be so casually disregarded? The evidence is clear. Meitner's contribution was not just crucial, it was the defining moment. Without her, nuclear fission would have remained an unexplained curiosity for months, perhaps years, and its profound implications might have been delayed indefinitely. This wasn't merely an oversight, it was a deliberate act of historical erasure, rooted in the prejudices of the era. You can no longer look at the history of nuclear physics at the very dawn of the atomic age and see it as a clean, straightforward progression of discovery. You now recognize it as a profoundly human story, fraught with the immense pressures of war, the insidious forces of prejudice, and the often unacknowledged brilliance of those whose voices were silenced. The image of the solitary male genius in the lab, a cornerstone of so much scientific myth-making, shatters under the weight of this evidence. You see instead the collaborative networks, the crucial exchanges of ideas across borders and political divides, and the heartbreaking truth that sometimes the most profound insights come from those deliberately pushed to the margins. Lise Meitner's story reveals not just a missing name from a textbook, but a fundamental flaw in how history itself is often constructed and remembered. This is the real history of nuclear fission, a truth that demands to be heard. And there are so many more untold narratives, so many other figures whose extraordinary contributions have been deliberately obscured, waiting to emerge from the archives and challenge everything you thought you knew.